All right, let's get into it. Have you ever picked up your phone, or really any piece of modern tech, and wondered how all those tiny little components inside actually talk to each other? Well, it's not magic. It's a set of really elegant, invisible languages.
And that's the big question, right? You've got a processor that needs to get data from a sensor, a memory chip that needs to store information. All of this requires a constant, reliable back and forth. The real challenge is, how do they all do it without just creating a mess of electronic noise? The answer is, they speak in protocols. You can think of protocols as the grammar and vocabulary for all this hardware. And today, we're looking at three of the heavyweights: I2C, SPI, and UART. These are, without a doubt, the backbone of most embedded systems. If you understand these, you really understand how modern electronics work.
So before we put them in a ring and see how they stack up against each other, let's get a quick blueprint for each contender. We'll take a look at what makes each one tick, starting with I2C.
First up is I2C, which stands for Inner Integrated Circuit. Now, this protocol was designed with two things in mind: simplicity and scale. Its biggest claim to fame, its whole reason for being, is that it can connect a whole bunch of devices using just two little wires.
So let's break that down. You've got just two wires. SCL, which is the clock line. That's kind of like the system's heartbeat, keeping everything in sync. And then you have SDA, which is where the actual data travels. But here's the clever part: the addressing. Every slave device, like a temperature sensor, gets its own unique address. The master, which is usually your main processor, just calls out that address, and only the device it's calling for pays attention. It even has a built-in acknowledge signal, which is like a quick roger that to confirm the message was received.
Okay, next up is SPI, the Serial Peripheral Interface. And if I2C is all about simplicity and connecting many devices easily, SPI is really all about one thing: pure, unadulterated speed. This thing is built to move a lot of data and to move it very, very fast.
SPI gets its speed from its four-wire setup. You've got the clock, SCLK, just like before, but then it has separate, dedicated lines for sending and receiving data, MOSI and MISO. This means it can have a two-way conversation at the same time, which we call full duplex. And instead of I2C's addressing system, the master uses a special slave select wire to activate one specific device. Think of it like this: I2C is a party line where the master calls out a name, but SPI gives each device its own private phone line. It's a really important difference.
And that brings us to our final contender, UART. Now, the most important letter in UART is that A, because it stands for asynchronous. This is kind of the original gangster of the three, the simplest of the bunch. It's designed for direct, one-to-one chats without needing a shared clock signal to keep everything in sync.
So you might be asking, how does it work without a clock? Well, it's all about a prior agreement. The two devices decide on a communication speed ahead of time. That's called the baud rate. Then, the sender wraps each little packet of data with a start bit and a stop bit. It's like sending a letter. The start bit says, "Hey, incoming message," and the stop bit says, "Okay, that's the end of it." The receiver sees that start bit, starts its own internal timer, and just reads the data at that speed they already agreed on. It's a simple system, but it's incredibly reliable.
All right, we know the players. Now it's time to put them in the ring. Let's look at the tail of the tape, comparing them across the most critical features to see where each one really shines and where they kind of fall behind.
First up is timing. I2C and SPI are what we call synchronous. The master device is like a conductor leading an orchestra, sending out a clock pulse that tells every slave exactly when to read or send each bit of data. It's super precise. UART, on the other hand, being asynchronous, has no conductor. Instead, it's more like two musicians who just agree to play at the same tempo, that's the baud rate, and then they just trust each other to stay on beat. Now this right here is one of the biggest trade-offs you'll see. I2C is just incredibly efficient with wiring. Two wires, and you can connect well over 100 devices. This makes it a dream for a circuit board that's packed with a bunch of different sensors. SPI, while it is fast, starts to get messy. You need the four base wires, of course, but then you need one more wire for every single new device you add. Your main chip can run out of connections or pins pretty darn fast.
So what about the flow of the conversation itself? Well, I2C is half duplex. The best analogy is a walkie-talkie. You can talk and then you can listen, but you can't do both at the same time. You have to say over. SPI and UART, though, are full duplex, which is much more like a telephone call. Both parties can talk and listen at the very same time, and that ability to send and receive simultaneously is a huge part of why SPI is so fast.
And speaking of speed, this is where the differences between these protocols go from noticeable to just
Dramatic. Let's actually look at the numbers and see who wins the race.
Yeah, this chart pretty much says it all, doesn't it? Down on the left, you've got UART and I2C. They're totally fine for a lot of jobs. But then, look all the way over on the right. SPI is just in a completely different universe. It doesn't even have an official top speed, and it can easily push past 100 megabits per second. For anything that needs to move huge chunks of data and do it now, it's really the only option.
So, with all these different strengths and weaknesses, where do we actually find these protocols out in the wild? Let's connect all this theory to some real-world examples.
Okay, so I2C's skill at handling lots of devices with just 2 wires makes it perfect for something like a weather station, where it's reading from temperature, humidity, and pressure sensors all on one board. Speed isn't critical there. SPI's incredible speed makes it the go-to for things that move a ton of data, like reading from an SD card or updating the pixels on a high-res display. And UART? Its beautiful simplicity makes it a rock-solid choice for connecting self-contained modules like a GPS or Bluetooth chip back to a main processor. So after all of that, we have to ask, which one is the best? How do you actually decide which protocol to use when you're building something? Let's boil it all down to a final verdict.
And here is the most important thing to remember. There is no single winner here. The best protocol is always, always the one that best fits the job you need to do. It's a classic engineering trade-off, balancing speed, the number of devices you need, and the hardware complexity you're willing to handle.
This table is really your cheat sheet. It lays all the trade-offs out bare. You need the absolute highest speed? You pick SPI. But look at the cost. You're dealing with 4+ wires, and that wiring gets complicated fast. Need to connect a whole network of sensors as simply as possible? I2C is your best friend with its 2 wires, but you're accepting a medium speed. And for a simple, bomb-proof connection between just 2 devices, you just can't beat the simplicity of UART. It's all about matching the protocol's strengths to your project's needs.
Look, each of these protocols is a really powerful tool in your toolbox. And by understanding these core differences in speed, in wiring, in their whole style of communication, you can make the right choice every time. You can make sure your components have a clear, efficient, and reliable conversation. So the only question left is, what are you going to build?